Welcome to Chapter 12. We're now talking about sound, and this is Section 1, Part A. And we're going to talk about the sound wave, the production or how it's made and its characteristics. So what we're going to do is we're going to explain how sound waves are produced. We're going to relate the frequency to the pitch, and we're going to compare the speed of sound in different mediums. We're also going to relate plane waves to spherical waves. So, first, we need to remember that longitudinal waves involve a part that has the compression, where the particles are closer together, and the rarefaction, where particles are further apart. So sound is a longitudinal wave. Right, let's see if we can remember how to spell this word here. Okay, and longitudinal waves are also sometimes called pressure waves, because these areas here of the compression is an area of higher pressure, and then these areas here are lower pressure. So this is from your textbook, and it's a good picture because it shows how sound waves are produced. So this is called a tuning fork, okay? And if we just ping the tuning fork, if we just hit it with a soft mallet, then what happens is the top part here vibrates back and forth. And so that's what's blown up here, is it'll move this way and that way. So you could think of as it gives off the sine wave, right? If it's moving this way, it's pushing all those air particles closer together, so you end up with the compression, okay, or an area of high particles and dense pressure. And then as it moves away, suddenly there's all this space for the air particles, and so that gives us the rarefaction. And so as it repeats back and forth, it creates compressions and rarefactions alternately. So, as we said, these are longitudinal waves, okay? And just something to help you as we go along through the rest of Chapter 12 is you may want to take a minute to review how a graph of a longitudinal wave is created. So you can also look back at the 11.3b video. The other thing I want to suggest is that you take a moment to check out how a speaker works. The link is here. It's also in your Chapter 12 folder in Schoology, so you can check both places, and it just connects how a speaker works either in your headphones or for your music anywhere, and how sound waves are made. So now that we've seen how sound waves are formed and the kind of wave that is produced, we're going to look at the characteristics of sound waves specifically. So audible sound waves, and this word here, audible, just means that we can hear it. Okay, so we'd say that humans, let me make this look more like an H, humans can hear. That's what the word audible means. Okay, and that range is from 20 hertz to 20,000 hertz. So remember, hertz is a unit of frequency. Okay, and frequency just means how many times a wave waves per second, right? Because the hertz is equal to 1 over seconds. So this means the wave waves 20 times per second, and here 20,000 times per second. So just to give you an idea, if it's 20 hertz, and I'm going to draw this one in blue now, a 20 hertz wave would be really kind of, we could almost think of it as slow, but it's not slow. And then a 20 hertz wave would be like this. And of course these aren't to scale, but it gives you an idea. Now, sound waves below 20 hertz are called infrasonic, okay? So if they're below what we can hear, they are infrasonic. So sonic is just a word that we use connecting to sound. This is a good word to become familiar with. So it just means it's connected to sound. Okay, and then waves above 20,000 hertz are called ultrasonic. So we have infrasonic and ultrasonic, and these would be ones above what we can hear. One thing is that other animals, though, can hear these waves even if we cannot. And I really want to point out that even though we cannot hear them, the waves have the same characteristics as audible sound waves that we can hear. So even though we can't hear them, they're still sound waves. So here's just an example of the different ranges that different animals can hear. You can look here and you can see humans. So our range here it says 20 hertz to 17,000 hertz, although the previous slide said 20,000. So there's a little bit of a variance, and some people can hear different ranges. But you notice dogs can hear up to 30,000 hertz, right? Cats all the way up to 45. So this is why we can have whistles that dogs can hear, but we can't, right? And a whale starts above ours and goes way above. It can hear all the way up to 80 kilohertz, so 80,000 hertz. Bats, of course, have a huge range because they use sound to tell where they're going, right? And even elephants have very similar ones to ours. They just have slightly less for their high range. So lots of different animals can hear different things. So even outside of what we can hear, these are still sound waves because they're still pressure waves in air. So one word that we use to describe sound waves is called pitch. And pitch is just what we describe as how high or low a sound seems to us. So if we go back to our range, right, things in the 20 hertz to us sound low, and so we would say it has a low pitch. Okay. Things on the 20,000 hertz range, though, okay, sound high to us, and so we would say they have a high pitch. So this is pretty easy. Just if it's a lower number, it has a lower pitch. If it has a higher number, it has a higher pitch. And pitch is related to the frequency, which is just the example that I gave you there. So the other thing we need to look at is the speed of sound waves. As we said before, sound is a mechanical wave, which means it needs a medium, and that medium is air most of the time. But really, it can be any material. Sound travels through water and through solids also. It's why you can hear through a wall. But the speed of sound depends on the medium and the temperature. And it's typically faster in solids and liquids than gas. So let's look at an example of this. Okay. So here I just kind of have some fun little pictures, right? You could think of, this is our picture of air, right? Then we've got water, and then I put a picture of an iceberg here because this is ice. So that is our solid, okay? We can also think of that as being examples of solid, liquid, and gas, okay? So I'm going to go ahead and write those words here too. So we've got a gas, we've got liquid, and we've got a solid. And it looks like that one's kind of hard to see. Solid. Okay, so what happens, okay, is in air, we know that the speed of sound is roughly 334 meters per second. Okay, so what means is that speed, okay, we're going to call that V, right? V will get bigger in liquid, and it will get even bigger in solids, okay? So it increases as you go along. Now remember, we have this equation that relates the frequency to the wavelength, okay? So what happens is it turns out that the frequency of different waves is constant. So frequency is constant. So that can't change. Okay. So if our frequency is constant and we increase the velocity, then what that means is that the wavelength must increase too. So if we start with just some wavelength here, it's going to have to get bigger also, and bigger even here also. So if we kind of looked at a picture of each wave, we might start with something that looks like this, right? And then it transfers to water, and that wavelength is going to get bigger. And then it transfers to a solid, and it's going to get even bigger, okay? So in each of these, the wavelength increases, okay? I'll just draw a big arrow, okay? So as speed increases, wavelength increases. But the frequency is constant. And we're going to find out that this is true for other types of waves and other mediums later in another chapter. So that is the end of the first part of Chapter 12, Section 1. We will get a chance to see a tuning fork in class, and I will see you guys there. Please let me know if you have any questions.